solution to linear Schrödinger equation. This threshold p greater than 2. Let's first look at why is this range p greater than 2n over n minus 1. So when p is infinity, this is an easy estimate because I was told that I shouldn't write a note. Right here. So when p equals to infinity, the continuum is bounded by one number. But this supported from the unit sphere, and this is generally bounded by some constants times. So we know that this restriction estimate holds true for p equals to infinity. And this range, this optimal range of p, that's p greater than 2n over n minus 1, something about the curvature of the sphere. So it comes from that the Fourier transform of the uniform measure of the sphere behaves roughly like x to the minus n minus 1 over 2. The two-dimensional case of the conjecture was solved by Feldman and Jacques-Louis in the 1970s, and the higher dimensional case and greater or equal than 3 remains open. So today we are going to survey the developments of around this conjecture and how it's related to different areas of mathematics. So in the 70s, when people are solving the two-dimensional case of the conjecture, they developed a method called the TT star method that showed some partial progress on this conjecture. They showed that the restriction estimate in Rn holds for p greater than 2n plus 1 over n minus 1. And this is not yet the optimal range, but such kind of estimate is also called the Streetcast estimate, has been widely used in differential equations. In 1991, Jean Bourgain realized that such function can be decomposed in a sum over simpler functions called wave packets, and this is called wave packet decomposition. This decomposition enables us to connect the understanding of such functions, the oscillatory integrals, to geometry about tubes. So the wave packet decomposition says that in a large ball of radius r, so the picture on the left-hand side is all happens in a large ball of radius r. One can decompose the function EF into sum over EFT. Each T is a tube of length R, radius R to the 1/2. And this blackboard T means a set of tubes of length R, radius R to the 1/2. Each EFT has some oscillation, but its absolute value is roughly a weight function, some weight times the indicator function of the tube. So it means that each EFT lives on this one of those tubes. It oscillates. The direction of this tube is related to some support of F. So the picture on the right-hand side describes how we do the wave packet decomposition. So very quickly, the wave packet decomposition is essentially partition of unity on both sides. So first, we decompose F into the support of F into a union of those caps. And this F equals to sum over F beta is just partition of unity. Each beta is a cap of radius R to the -1/2. And once we look at beta and then we take the Fourier transform, then this is we call EF beta extension of the beta. It can be decomposed. For example, this yellow, suppose theta is this yellow cap, then it can be decomposed into sum over ft, where ft is each ft lives on this yellow tube that's normal to yellow type on the right hand side. And this is where, so this part EF theta equals to sum over EFT is again like a partition unity on the in Rn. And the reason is by uncertainty principle, if a function has the support on the small cap, then if one cannot really distinguish this function in this dual convex set, that's like a tube. That's like this tube. So the takeaway from this wave packet decomposition is that such functions are very complicated to understand, but it could be decomposed into some building blocks, and each building block is a wave packet called EFT. And in order to, so we understand very well each EFT, but we don't understand that well how they sum up together. So to understand how they sum up together, there are two components. They're not independent, but the two components are the geometry of tubes. So we have a collection of tubes, and we want to understand whether they overlap a lot. At the places where they do not overlap, then the functions are relatively easy to understand. Where at the places that many tubes go in, then this function could be very large. And at those places where there are many tubes passing through it, there is still oscillation going on. So it's not clear that the function is going to be necessarily large, because they could be constructive interference or the opposite, like making it even smaller. So this is the oscillation that one has to worry about. So for today, I'm going to mainly focus on how the geometry of tubes could help us understand such functions. So speaking about the geometry of tubes, so the size restriction conjecture, the conjecture we just saw, implies conjecture in geometric measure theory, the Kakeya set conjecture. It says that if a Kakeya set in Rn is a compact subset that contains a unit line segment in every direction, and the conjecture is based that the Hausdorff dimension of a Kakeya set. This purely geometric conjecture is closely related to the restriction conjecture in Fourier analysis. And it is also a consequence of a very difficult conjecture in number theory called Montgomery conjecture on laser acquisition polynomials. So it's connected to, already itself is connected to many different areas of mathematics. So how to visualize and like Hausdorff dimension. So there is a more straightforward discretized Kakeya set conjecture about geometry of tubes. And this discretized version implies the Hausdorff-dimensional version via some classical geometric measure theory argument. So the discretized conjecture says that if we have a set of delta tubes has radius delta and length 1, with 1 in every delta separated direction, means that we have a delta net, and then every point in the delta net we have 1, 2 in this direction. Then the union of the tubes in a collection has volume greater than an arbitrarily small power of delta. Sometimes we also call those such union of tubes a Kakeya set. So now let's go back to the history of the restriction conjecture, and later we'll see that how understanding this tube overlap make a big part of the understanding of the conjecture. Okay. Now we are in 1991. John Buchan discovered this wave packet decomposition, so that it links the analysis of such functions with the geometry of tubes, and now people have been developing different tools to understand the geometry of tubes. From the year 1995 to 2003, people have been exploring the following idea. So one could sort the points and the tubes according to, for example, one could sort the tubes according to the location of some points on it. So let's go back a little bit. What are the points? Here we said that a function is a sum of wave packets. And we can see already from this picture, not all points are equal. So there are some of the points there, like some of the balls where there are a lot of tubes passing through it. And there are some of the balls where there are only one tube passing through it. So one could sort the contribution of one could sort the collection of balls according to their contribution. And so there exists, for example, there exists a sub-collection of those balls where each ball has about the same amount of contribution to the LP. Yeah, and these are the balls that are here, for example. Let's plot those. And so those are the balls that are interesting for us. And already, so now we could do some further decomposition. So this is to identify what are those balls, I just pigeonholing step. And once we have identified a collection of the balls, and each ball has about the same weight, about the same contribution to the function, then we can sort further. The sorting is according to, for example, whether a typical pair of the tubes passing through this ball form an angle of approximately 1. So this is called bilinear. For example, this ball is bilinear because the two tubes passing through it has angle of 1. And this ball is not bilinear because the two tubes passing through it has a small angle. And also one could sort the collection of tubes according to the location of the balls. For example, this tube is not 2 ends because the collection of the balls that on it lies in a small segment. And this tube is 2 ends because the balls are not concentrated, they are spread into 2 ends. So the key idea due to originated from Wolf and was fully developed in Tao's work, says that one can reduce the problem to bilinear or 2 ends case without loss. And so why are we decomposing them into these two cases? There is some advantage about being bilinear 2 ends. Means that, so if two tubes intersect in a bilinear way, then they intersect only at approximately 1 volt. But if two tubes have a small angle, they are not bilinear, then they could intersect into many balls. For example, here, they in fact intersect into some segments that we can pack a lot of balls on. Similarly, if we are only interested in 2 ends tubes, then we can have a very nice, not very nice, but have a reasonable upper bound on the number of tubes that is bounded by the number of balls squared by Cauchy-Schwarz. Because for this not 2 ends tube, there could be many other tubes passing through the same collection of balls. So using this idea and also this simple Cauchy-Schwarz consequence, Tao proved.
What's the 2 n?
Yes. So I'm saying it in words, but later we'll see a rigorous definition. 2 ends just means that the balls on this tube are not concentrated in a small segment. They spread out into 2 ends. That's this. And so using this idea, Tao proved that the previous restriction, so the restriction estimate holds for any p greater than 2 times n plus 2 over n. And so this is still not as good as the conjecture found. So the conjecture is p greater than 2n over n minus 1. So this is 2 over n minus 1, and this is 4 over n, which is this figure. So this is a very nice idea, and it gives almost a lossless reduction, saying that we can just consider the problem consists of only bilinear points and two end strips. And this is also a nice Cauchy-Schwarz bound, but are they the best possible? It's not clear. But for a long time, people were not able to improve this simple bound. And then in the year 2014, in harmonic analysis, a lot of things happened in 2014. This is thing. And we'll see another thing very soon. Another important paper very soon. So Larry Guth introduced this polynomial partitioning method in harmonic analysis and into the understanding of tubes. So the idea of polynomial partitioning is that if we have a collection of tubes and also a collection of balls, so to understand how much they overlap, one could use a zero set of polynomial to cut the space, for example, to cut the space such that the balls distributed evenly in each connected components that are cut out. And this is like partitioning the space using zero set of polynomial is a powerful idea. And this enables people to improve the restriction estimate by a lot. For example, in higher dimensions, so asymptotically from the previous like 4/n, people were able to improve this to 2.59/n. And again, the conjecture is asymptotically 2/n-1. But what's still we have not yet been able to prove to push it to the end. But when people develop this method, there is something more. There is some question that people have isolated. That's I think that's how to say this particular question is like not as difficult as the Takaya conjecture. It's natural from the development of this method, and this question is: can one put a Takaya set inside a thin neighborhood of algebraic hypersurface? So this is much weaker than the Takaya set because, well, if one can put a Takaya set inside a thin neighborhood of an algebraic surface, the algebraic surface has a small volume, a very small volume. So here, by Takaya set, I mean the union of tubes. So, and then the union of tubes have a very small volume. So this is, if one managed to do that, this is obviously a counterexample to the Takaya set version. So for a while, it's not even clear whether this weaker version problem is true or not. And it turns out that one cannot put a Takaya set inside a thin neighborhood of a 100-degree algebraic hypersurface. So here, what I mean is that previously we think Takaya set as a union of delta tubes. I can just think of let's say delta neighborhood. This was proved this was conjectured by Guth and Zhao when they were trying to improve the Takaya set estimate in higher dimensions. And it was proved by Katz and Rogers using very surprising tools. That if they use real algebraic geometry, including Katz-Fitts projection theorem and Gromov's algebraic lemma. So, but borrowing very heavy real algebraic geometry tools, when they were able to show that polynomial neighborhoods of zero-set polynomial cannot possibly be contained in a Takaya set. So this kind of algebraic configuration is not and should not be a counterexample. We'll see that we have to use this later when we think about further geometry of tubes. So another important theorem that happened 2014 is in harmonic analysis is the Bourgain-Demeter decoupling. And here I'm trying to talk about the refined version of that. That's due to good research in myself and also independently by John. So the reason why I'm presenting this version is that this in some sense decoupling is a way to handle oscillation. And after people handle the oscillation, so oscillation just means that when we see a lot of wave packets intersecting at some point, and at this point there are like oscillation going through this point, one would want to see whether it's a constructed interference or not. So, and this version of the Bourgain-Demeter decoupling works naturally with the later incidence estimate that we are going to talk about. It works naturally about with the like how balls interact, intersect with the tubes. So let me try to present it. So this Bourgain-Demeter decoupling is a different way of estimating the LP norm EF. As we saw, the restriction conjecture is about estimating upper bound the LP norm EF. So what does this say? Already from the wave packet decomposition, we know that EF can be written as a sum over wave packets here. And also we have seen previously that after pigeonholing, we can focus ourselves on a collection of balls. So let's just call the collection of balls to be X. The X is a union of R to the 1/2 balls. The reason it's R to the 1/2 is because each tube has radius to the 1/2. And let's say M is the maximum number of tubes passing through each point. So all this geometric information about the balls and tubes. And then sorry, this was shifted a little bit, but then the decoupling estimate says that for any P greater than 2, then the impedance to N plus over N minus 1. We started by so this double squiggle means there will be some up to small powers of R that are going north. It's less or equal than M to the half minus T and LP norm and then we take the little TT. And since we know that if you take absolute value of the T, it's roughly some constant times the indicator function of T. So the term on the right-hand side does not have any oscillation. They are just about, let's say, about the number of tubes, also about weight. And after pigeonholing, we can assume they have essentially the same weight. In other words, we can assume CT equals to 1. And so this is just about how many tubes there are. Also the volume of one tube, which is something we know. And this is the number of tubes to a typical point. So M is roughly like the multiplicity of tubes. So that is should also say that this is only in X, but it's without loss of generality because one could picture to binary that boundaries the LP norm of in the whole space up to log 1 over log. So what decoupling does is it's like this bound. The left-hand side, we still have a lot of oscillation to control, and the right-hand side, we don't have any oscillation, but we still need to understand the relation between M and the number of tubes. So the right-hand side is how to go from the right-hand side to, for example, the LP norm of small f. which is the right-hand side of our restriction conjecture, is a matter of understanding the geometry of collection of tubes. I should also remark that this Wang decoupling theorem has a lot of applications in, for example, in number theory and also in PDE. So here I'm just presenting like this Wang decoupling theorem is useful for size restriction conjecture. So now let's see how the right-hand side is related to incidence for tubes problem. So incidence for tubes just means like how many tubes intersect one ball and how many balls on its tube. So this incidence for tubes problem is about the relation between the size of X, so the volume of X, the number of tubes through one point, the means multiplicity, and the total number of tubes. So there is by double counting, there is a different way to rephrase the problem. For example, we can define the shading of a tube YT just be the intersection of X in T. So the balls of X contained in T. And by double counting, one could also, after some pigeonholing, one could imagine the volume of YT, the subset of tubes, times the number of tubes is roughly the volume of X times R multiplicity. So to understand the right-hand side of this bound, we need to understand the relation between X, M, and the number of tubes. So after double counting, it leads to understanding the volume of YT and the number of tubes and the volume of X. So this is the problem that we are going to investigate for the lab and see how it is related to a different field in mathematics for the projection theory. So what do we know about the number of tubes and YT? YT just X intersect T. In principle, nothing. So the tubes come from function which can be arbitrary. YT just come from the set X after pigeonholing intersecting T. And so they are a general set of delta tubes and delta balls. And if you still remember the Wolff's 2n's reduction or the bilinear, one could maybe assume YT is 2n's, which is going to be the assumption that we made in the end. And then one could potentially assume that each point in each ball in X is bilinear. But that's all we know. But that's not enough. So one of the powerful ideas that happened with the LJLL theory in recent years is that one could find structure in a general set, tubes and balls, and this is some multi-scale decomposition. So the type of structure that's useful for us is called let's say finding the structure of some S-dimensional set. This is what we call a delta S set. So, which means that the collection of points, for example, in YT, is roughly a delta, roughly an S-dimensional set. So what does it mean? First, if we have a non-empty subset E in RD, the delta covering number E is like the minimum number of delta balls required to cover set E. And we say that E is a delta S set if for any intermediate radius R between delta S1 and for any ball of radius R, E intersecting BR has delta covering number less than R to the S times the delta covering number of E. This R to the S is a quantity size that how non-concentrate E is inside any ball of radius. And in particular, this implies if we take BR to be one delta ball in E, then this implies that the delta coverage is greater than delta to the minus S. So, and this is a way. So this is a discretized version of a set has dimension greater or equal than S. It roughly means that we need a lot of delta balls to set E, and the E is not concentrated in any ball of intermediate radius. So one can also parameterize the lines and define, let's say, S-dimensional set of tubes as just S-dimensional as the dimension of its parameter spaces, its parameters. For example, given A and B in R2n-1, A is in Rn-1, B is also -1. A line in is A0 plus B1 times T, and B comma 1 times T, T is in R. So when we have a delta tube, that is a delta neighborhood of such line segments, let's say inside a unit ball, then each delta tube corresponds to one delta ball centered at A and B, and then this will correspond to one delta. So when T is a set of delta tubes in Rn, so this gives us a union of delta balls. So we could, similarly, we say that T is a delta S set of delta tubes if ET is a delta S set. So then when we are given such kind of assumptions, when there is a conjecture in projection theory or in geometric measure theory called the Furstenberg set conjecture. And I hope to convince you that this conjecture is relevant to understanding the right-hand side of the Bourgain-Demeter decoupling, and therefore it's helpful for us to understand the restriction conjecture. So we said that to understand the right-hand side is about understanding the relation between the volume of shading and the number of tubes and the union of the shading. So this is exactly what the Furstenberg set conjecture does. But for now, the conjecture is only in R2. It says that if S is between 0 and 1, and T is between 0 and 2, suppose we have a delta T collection of delta tubes in R2. For any delta tube, we have delta S set of delta balls YT contained in T. So YT should really look like this is a tube, and then it should look like some union of delta balls. Then the union of YT has delta covering number greater approximate than delta to the minus S plus T, 3S plus T over 2, S plus 1. So all these terms have some meaning. This minimum is attained by S plus T if we have very few tubes, and on each tube there are a lot of delta balls in YT, then this term dominates. And the last term, S plus 1, becomes the minimum when we have a lot of tubes. And in each tube, YT is relatively small. So this term becomes the best when T is greater or equal than 2 minus S. So this term is the most interesting. It's when the collection of tubes is not too large or not too small. And this term has a sharp example coming from the lattice construction that I was interested in the time. I'm going to skip it. So this Furstenberg set conjecture is exactly trying to understand the same problem, but in R2. So we have a collection of tubes, and on each tube we have some subset, some subtraction of the ball set. And we want to understand how large is the union of those balls. So this is exactly the quantity X that appeared on the right-hand side that appeared in the decoupling estimate. So for this problem, there is a special case of this problem called sticky case, was solved by Thomas O'Connor and Pablo Schmerking, when the tubes organized in a roughly self-similar way. And the general case was solved by Kevin, a graduate student in Princeton, and myself. So using this conjecture solved 3 years ago, one would think, can it help us to understand the geometry of the tubes for the problem we have in decoupling? So to do so, we need to make things a little bit more general. Also, as I said before, the problem that come from decoupling, the sets that come from decoupling is for the function from the restriction estimate is a general set of delta tubes and delta balls, and one could find structure from those tubes, for example, delta S structure. So that this conjecture is not that special. But one should still go back using the structure we found and using the bound for the structured set to go back and see if we can prove something more general. So, and as we saw in Wolff's argument, the most general assumption that we can assume without loss is the 2n's assumption. So here is the 2n's assumption about YT. So YT, so this picture we saw it already. T is a delta tube and YT is a collection of delta balls on it. Its 2n's give the following holds. There exists epsilon greater than 0 such that YT is a delta epsilon set. It means that it's just slightly non-concentrated on smaller segments. And here we can still assume that the delta coupling number of YT is greater than delta to the minus S. So the coupling number is still the same as a delta S set, but the non-concentration property is much, much weaker. So joined with Shupeng Wu, we showed the same bound, essentially the same bound hold when T equals to 1 and when the assumption on YT is 2n. So this recovers the same Heisenberg bound. And this is useful because the 2n's property is the property we can get from Wolff's 2n's reduction. So this is not without loss of generality. And indeed, that's what we were able to apply back to the restriction conjecture. So we show that in R3, for any P, this is a P greater than 22/7. This might not sound that interesting number, but so the conjecture was P greater than 3, and the previous best known bound was P greater than 3.23, which uses a polynomial method. And this one is like P greater than 3.1 something. And we show that the restriction estimate in 3 holds. It also gives some asymptotic improvement for higher dimensions as well. So the point of this approach is that so this essentially the proof idea is just 1 page. If you black box 2 very heavy tools, so this restriction estimate that we obtained, we use naively this decoupling estimate to handle oscillation. So we applied. So the first step, we pigeonhole and find our interest in X. And then we apply Holder's inequality because the range of P we are interested in is different from the optimal range of the decoupling estimate. And we just apply Holder's inequality. And for the first term, we apply refined decoupling estimate. And once we have done applying the refined decoupling estimate, we are done with oscillation. And all we need to do is to plug in the previous incidence estimate that we obtained from applying this. Even though this is in R2, then we will upgrade it to R3 later. And then combined with the incidence for tubes estimate, we would conclude that such restriction estimate holds. So unfortunately, this is not sharp. So one reason for that is we sort of split the analysis of oscillation and geometry too early. So we just apply one step to nothing, and then and we are done with oscillation, and we just apply its geometry. So we might need to apply induction on oscillation together with the geometric estimate. Another thing is that this incidence for tubes estimate, what I mean is just the volume of X and the volume of the size of the living and the number of tubes. So the relation between these three terms, when we apply the kind of relation we apply to this restriction estimate was not sharp. So we apply this sharp estimate in R2 and combine with the Wolff's Hellbrush argument, some simpler not simpler, but combine with some non-sharp argument again for incidence tubes in R3 to obtain some partial results about the relation between these three terms. So one could hope that maybe some improvement would be better incidence for tubes estimate. So for the rest of the talk, I'm just going to present some guess or some conjectures eventually related to the kind of things we have seen before. So when we say better incidence for tubes estimate, we mean better relation between the number of tubes and the number of balls on each tube and the volume of union of those balls, which means like previously we only applied the two-dimensional Furstenberg set estimate. So what about three-dimensional Furstenberg set estimate? It turns out that in order to do that, just delta T set of tubes is not enough, because if we take all the tubes that contains in a plane, it's a delta 2 set because it's a two-dimensional set of tubes. And this is not interesting because in R3, all the tubes contained in the plane, where the union of plane is still a plane. That's not a big volume. So in order to give the right assumption on the set of tubes, we'll use something called some analog of the delta, the T-dimensional set. It's something that the tubes are not concentrated in any convex set. So we can say that a set of tubes satisfy the T-Frostman convex warp axioms if for any convex set U, the number of tubes containing U is less approximate than the volume of U to the T times the number of tubes. So we are able to prove very special case of that. That is when T equals to 1. And if the YT is the entire tube, then joined with Josh, we show that if a set of tubes in R3 satisfies one Frostman convex warp axioms, then the union of tubes has a volume greater approximate than 1, so greater than delta to the epsilon for any small power of epsilon. And this implies the Kakeya set conjecture in R3. And this implication is some sort of exercise, because if a set of tubes consists of one delta tube in every delta separated direction, then it's not hard to verify that such set of tubes satisfies the one Frostman convex warp axiom. means that the number of tubes contained in each convex set or each rectangular box is smaller than the volume of the rectangular box times the total number of tubes. And so similarly, we could also define what is called something Furstenberg set as conjunction in R3. That is, instead of taking the entire tube, we take a subset of tube YT. So we have similar conjectures where those numbers coming from like generalization of the graph example. And this is a more general version of the Kakia set conjecture, as we said. So this version, if true, it implies the Kakia set conjecture by setting t equals to 1 and s equals to 1. But in higher dimensions, those axioms are not sufficient in dimensions n greater or equal than 4, because we can find a quadric that contains like the quadric xy minus cw equals 1. It contains a 3-dimensional set of lines. So in order to fix this problem, instead of saying that the tubes are not concentrated in convex sets, we need to say that the tubes are not concentrated in semi-algebraic set. So we say that a set of tubes in Rn satisfies the T-Frostman polynomial Wolf axioms if for any semi-algebraic set U degree bounded by some large constant, the number of tubes containing U, in particular such U, could be without a neighborhood of quadric. The number of tubes containing U is by the volume of U to the T times the total number of tubes. But now, previously we said that this convex Wolf axioms, so if a set of tubes consists of one tube in every delta separated direction, then it implies the convex Wolf axiom. But what about, does it imply the polynomial Wolf axioms? So again, this, as we discussed before, this is highly non-trivial, and this is proved to be true by Cass-Rogers using real algebraic geometry. So all this is to say that indeed this is a reasonable assumption to add. And also this is a necessary assumption because of this quadric containing a lot of lines. And this is a reasonable assumption because for the set that we are interested in, the Kakia set, the tubes in the Kakia set also satisfies the Frostman polynomial Wolf axioms. So similarly, we could ask similar Furstenberg set conjecture in higher dimensions. Suppose we have a set of delta tube, it satisfies the corresponding T polynomial Wolf axioms, and on each T, we have a delta S set of balls. And what is the union of those balls? This conjecture, again, if it were true, it would imply the Kakia set conjecture by setting T equals to 1 and S equals to 1, and also by using this the theorem of Katz and Rogers, saying that no Kakia set can be put in the neighborhood of algebraic hypersurface. Yeah, stop here. Thank you very much.
Thank you. Thank you very much, Wang, for this very nice talk. Are there questions?
So I have a question. So if the tubes are not exactly straight, is it working a bit or?
Yeah.
That's a great question. So it depends on how you define the family of tubes. So in harmonic analysis, there is some more general operator than the restriction operator. So there's something called Hammond operator. And similar, so that is the functions instead of, so the restriction function estimates, it's about like functions. The function of this form, and the phase function is basically x comma t dot plot with some some surface. And if you replace this by some other like nonlinear phase functions, add some natural assumption on it, it's this is a more general operator called Pomander operator. And for the corresponding carcass coming from those Pomander operator, there are curved tubes. And it was so Jean-Baptiste provided a quantum sample saying that for those curved tubes, corresponding carcass conjecture is false. So it really depends on how you like what's the family of the curved tubes you are interested in. So maybe for some family it's still possible it's true.
You said close to one direction, but was it?
No, actually, the common example Wolfgang found is so the tubes are concentrated on near algebraic surface, and the tubes are curved in some algebraic way. They are pointing so-called different directions. But
Other questions? Thank you for all these very nice lectures, which will be put on the YouTube channel of the LJLL shortly, so that everyone can see them again. I have had some questions about that.